Okay, how's everybody today? Sorry about the snow day. I would much rather have been in class with you Friday than to have to make a video to get us through Monday. The problem is that I am involved in the selection of the new principal, and Monday is the day when all of the interviews are taking place, so I'm involved with that throughout the day. It's supposed to be a long day. But as a result of that, I can't be in class with you guys, which is not what I would prefer. So this little video here, I'm going to have a couple of them, I think. This video here is to get us through the FRQs from the test, and I believe our substitute has handed out the test to you, or ought to have by now. So first question that we have was this one. And it's a classic. I'm going to give you another problem much like it at the end to work on. But this is typical kind of a setup. We have a ramp. We have a thin hoop, which tells us that all of the mass is concentrated out at the perimeter. And it's given these parameters: mass m, radius r, rotational inertia mr squared. That is accurate. That maximizes it for a hoop, doesn't it? Is released from rest at the top of the ramp of length L. Now that's the length of the ramp, not the length of the base of that triangle. The ramp makes an angle theta with respect to horizontal. The table is height h above the floor. That is not the height of the potential energy h for the ramp, at least not yet. And then assume the hoop rolls without slipping. We know the implications there. That's the V equals R omega piece that we always have to trot out in these kinds of problems. And then express all answers in terms of given quantities and fundamental constants. I wanted to underline that because it turns out that some students, whenever they see G, they automatically drop in 10 or automatically drop in 9.8. And whenever you see fundamental constants, you can just let G remain as the letter G. You don't need to drop a number in there. And the only implication in this problem, if you did that, if you didn't leave it as as G but translated it to a number, is you had a little different simplification on a couple of the problems here, which made for challenging grading. So I would say that the designers of the problem asked you to leave it in terms of G, really so the graders would have an easier time of it, not that it makes a difference ultimately in the answer. Okay, first problem, we have derived an expression for the acceleration of the center of mass of the hoop as it rolls down the ramp, so we have some thinking to do there. And then part B, derive an expression for the speed of the center of mass when it reaches the bottom. And this is kind of the split in the problem. You have parts A and B, and then you enter the second phase, which is where the hoop rolls a little ways across the table. And that's a gentle transition. It's assumed you can sort of see a curve in there, and then the hoop leaves the table and then descends only under the influence of gravity, and then eventually hits the floor. And that's what the parts C and D are. Derive an expression for the horizontal distance from the edge of the table to where the hoop lands on the floor. Excuse me. And then part D, suppose the hoop is now replaced by a disk having the same mass and radius r. So a disk is sort of solid all the way through. How will the distance from the edge of the table to where the disk lands on the floor compare with the distance determined in part C for the hoop? Less than, same as, greater than. It's the three bears. And then we need to justify our response on that. So I'm going to ask you to keep this handy. I need to remove this from the screen. But I'll probably draw a quick little sketch. Let me get out my handy dandy ruler. Okay, I'm going to move that there. And if you don't mind, see, I'm looking pretty casual. It's Friday. It's Friday around noontime. I'm here at the building recording these. Okay, here's our ramp. The hoop is up there. We do have theta. Suppose we have a tabletop. We could probably drop that in. And this will do for the first part of the problem, just a quick sketch like that. And I want to have let's say I have a red pen. I got a new red pen. And I'll keep orange and green handy in case we need to in case we need to, improve our drawings a little bit. Little things here, we have distance L, and that is, from where the hoop is to the bottom of the ramp. And the variables we are given, we have the mass M. The hoop has radius capital R. I'm going to try to be a little diligent about caps and lowercase in this problem. You can't always, but I'll try. Let's see, and then we know we have G, and then fundamental constants. This phrase, fundamental constants, also is supposed to convey the possibility of using trig ratios. So all that, the sines and cosine stuff, that falls under the category of fundamental constants, believe it or not. Okay, so now it turns out we have two approaches. Actually, there's three approaches, but I think there are two that would naturally occur to you. One is that we have, a component of gravity, which would be mg sine theta, pulling the hoop down the hill. We have a friction force acting contrary to that direction, and the sum of those two forces would result in the, that would be the total force going down the hill, and from that maybe we could back out gravity. Another option would be to focus on the point of rotation, which is the point of contact where the hoop meets the ramp, and to calculate torque about that point, which would mean using the mr squared, and then we'd have to add to that a parallel axis shift. I can make this bigger, couldn't I? And we could add to that a parallel axis shift, so then we could calculate torque equals I alpha, and then the alpha that we get out of that is exactly the alpha that we need, and then we could do some mumbo jumbo that way. So let's do the first approach that I mentioned. We'll do that first, and then see where that takes us. Give me just a moment. I need to get my scoring guidelines handy. Yeah. Okay. All right. So we'll call this approach one, and I'm imitating scoring guidelines on this. They actually offered three different approaches. And what should we call that? We'll call that sum of forces down the hill, or down the ramp. And that will be our name for this approach. Let me back this out just a little bit. Okay, so that means we sort of need a free body diagram, I think, would be a good idea. So we have we have mg down, we have a normal force going perpendicular to the hill. We also have friction, and I'll imitate their notation. They just use a cursive F or an italicized F. And we know that we have the ability to resolve weight into two components. We have this component, which is mg sine theta. That's an old friend. We've seen that for a long time. And then there's another component that we don't have to make such great use of in this problem, which would be mg cosine theta. And that makes this angle right in here, I don't know if you can see where my pen is, that is also angle theta by similar triangles to this angle theta here. Okay, so how about Newton's second law? We would say the sum of forces along the ramp, I'll just write ramp, is equal to m times acceleration down the ramp. And I've already made a mistake. I use lowercase m, but this is sort of just setting up the problem. We'll do some substitutions in our next step here. So the sum of forces, let's describe down the hill as positive, and we'd have, let's see, capital M G sine theta minus the force of friction is equal to capital M mass times acceleration of the center of mass of the hoop. Okay. Now, let's draw a little bit bigger drawing of the hoop. Here's a little bigger drawing of the hoop, and this is where friction is acting. It's going like that. The radius comes out of here. There's capital R for radius. This is friction. And can you see that that is a torque? In fact, that is the very torque that causes this thing to rotate. And of course, when that torque acts, it's going to cause it to rotate clockwise. Right? So that would be, I guess we'd call that a negative torque if that was a concern for us. So let's use a definition of torque. Torque is equal to force times moment arm, which is equal, in this case, to the force of friction times R. Now we also know that torque is equal to I alpha. That's that sort of double equation thing that we mentioned once upon a time. So I can set this expression equal to I alpha, which is kind of fun. Now I can, how about if I solve for friction right here? So friction is equal to I alpha over R. Good so far? Okay, friction is that. So now I see something I can drop into this thing up here. So I'm going to take this expression and drop it in up there. But before we do that, let's do the rolling motion conversion piece, and in this case, it's that alpha is equal to A over R. I'm using capital R right there. A over R. Now, linear acceleration of the center of mass is equal to R alpha. So let's drop that into here. This equals I A over R. Now that's the R that was already there, but we need to add the R that's right here. And that, in turn, gives us I A over R squared. Okay. Yeah, I'm just looking at my work. I think I'm okay at that point. Okay, so now let's take this chunk right here, which is force of friction, and we're going to drop that into right there. And we get mg sine theta minus I. Oh, I can substitute for I, can't I? Because I know I is mr squared. So I'll do that right now. Minus mr squared, there's I, times A over R squared. Okay, that's that R squared right there. And that equals M times A. Now let's simplify what we can here. I see R squared can go away, top and bottom. And I see A appears, M appears everywhere you look, but I also see that A appears in two places. So how about if we first divide everything by M, that goes away. And we recopy for clarity. So G sine theta minus A, everything else has been consumed by dividing things away, is equal to A. That looks kind of strange. But let's gather our A's on one side, and I have G sine theta is equal to 2A, and that means that A is equal to G sine theta over 2. That bigger. I'm sorry, I'm looking at a closer screen. You guys really should be able to see that better. Okay, so that's the answer to part A. Label this as part A. And while we're at it, we're going to do part B. And you'll see why. A and B, turns out together there's 8 points in part A and B, but we need to sort of grade them together. So while I'm here, I'm going to get out, I think, a kinematic equation. So I think that's the easiest way. So for part B, part B is asks us to find the velocity when it gets to the bottom of the ramp. What does it say? Derive an expression for the speed of the center of mass of the hoop when it reaches the bottom of the ramp. Okay, that is A of the center of mass. We just found that. So let's use a kinematic. How about V squared final equals V squared initial plus 2A delta X. Now, I'm putting that in quotes because in our drawing here, x and y are a little bit awkward. You know, maybe it makes sense to think of that as y right now and that as x, but I'm just going to replace delta x with L. That's not a great leap right there. It starts from rest, so that expression goes to 0. And I can just solve this and clean up a little bit. V final is equal then to the square root of 2AL. And I think we have enough to do some substitutions here. Square root of 2, now the A from, where did it go? Right here. So it's 2 times G sine theta over 2 times L. Do a little cleanup. The 2's can go away. And I have V at the end of the ramp. Oops, I'm off the screen there. V at the end of the ramp is equal to the square root of, how about GL sine theta. Okay? And this, all the work that we've done so far is worth 8 points. So 5 points was this first component, part A, and various things in there got you points. And then part B in this approach was 3 points. Okay? So there's one approach. So let's do it a different way. And I'm going to number these sheets. I'll hang on to them in case anyone wants to look at them later. What I want to do is show you the different approach, the other approach, which is probably more like the one that I first demonstrated in class when we did a ramp problem. I think that might have been the first problem we did in rolling motion. Here's our ramp again. And imagine that this, I think to illustrate this idea, I'm going to just sort of imagine that this keeps going so that I can draw a nice big circle. If I were a better teacher, I'd have something to trace that was circular, but I don't know, the end of a glue stick. Well, kind of. Okay, well, I'll work on that part of my delivery some other time. I drew it nice and big because I want to show what happens when we talk about torque about that point right there. Remember, in the instantaneously, the hoop is pivoting about that point. Well, here is the center of mass. And we know that I about the center of mass is equal to mr squared. But if I want to calculate some properties of this thing as it moves about that point, we need to add to that a parallel axis shift. Well, the distance we're shifting our center of rotation is a distance r, and the mass is still the same. So what should I call that point? How about if I call that point 0? I about point 0 is equal to I about the center of mass plus, our usual md squared, which in this case would be mr squared for I about the center of mass plus another mass times r squared. So that turns out to equal 2 mr squared. So I about the point of contact is 2 mr squared. And that was worth a couple of points. Now, I didn't do something that, well, I'll do it right now because we have to begin from a starting concept. So torque. Let's use torque. Torque is equal to I alpha. More precisely, the sum of torques is equal to I alpha, because it's possible you could have more than one thing acting on this. We don't. We just have weight. So let's look at a triangle. I want to look at where weight acts. Weight goes straight down. Okay. I'm just going to make it a big old mg. Sorry, I strayed into my equation right there. There's mg. There's a force, and if there's a force and it's causing a torque, there must be a moment arm around here somewhere, and that moment arm is perpendicular to it, passing through the center of rotation. Okay, so I don't know if you can see that. Let me make it big. Here is the force coming straight down there. There is a moment arm, and to add an angle This angle right there is angle theta. Okay, so the torque, force times moment arm, we need to find that little red segment. That's the moment arm, because we already have, we're moving from now to torque. I'll put it on the left side of the equation, is force times moment arm equals I alpha. The force is mass times gravity, and moment arm, let's see, if this over here is r, and that's theta, that over r is a sine of theta. So that little component there is r sine theta. That is our, capital R sine theta, is equal to I, which is 2mr squared, 2mr squared times alpha. Right. So this is another approach, and it looks to me like we can start some cleanup here. Make sure I haven't left anything off the table that should be there. I think I'm okay so far. RMG, 2mr squared. Okay, but now we can do our rolling motion piece. Alpha is equal to A over R. So I can replace alpha with A over R. That's a point. It's funny. That is very frequently showing either alpha equals A over R or A equals alpha R, or the equivalent for V, V equals R omega, things like that. That's almost always worth a point in scoring. So let's clean this up one more time and move over here away from my red borderline. Mg R sine theta is equal to 2mr squared A over R. Okay? And what are we solving? We're solving for A. And the nice thing is it only appears once in this business. So let's see. We can clear out that R. We can clear out that R. We can clear out the exponent. We can divide both sides by R, and all the R goes away. We can divide both sides by M. The M goes away. And I think we're there. Solving for A, there's a 2 right there. So I'm going to have to divide both sides by 2. A is equal to G sine theta divided by 2. And that's the correct answer. So all the work that we did up to this point on this part of the problem, that would have been worth. How did they approach it? Well, so far that would have got you 5 points. Okay, if you'd used this approach right here. Okay, so we just have that one other part, which is to find the velocity as at the bottom. And now that we have acceleration, we would do exactly the same thing that we did over here. We would have just used a kinematic equation, because it is a constant. Everything in there is a constant. So if you're troubled by the question, can I use constant acceleration kinematics? The answer is most definitely yes. Okay, so we do this very same move, get the very same answer, and then we're on to part C. Okay, so I'll put for part B, I'll just say same approach as before. And like I said, I'll save these notes that I'm doing right now, and I'll if anyone wants to look at them, you're welcome to it. Okay, so now let's do part C. Part C says, derive an expression for the horizontal distance from the edge of the table to where the hoop lands on the floor. So I guess this sort of calls for another little sketch. We can make it a little bit tighter than we did before. Here's our ramp. Here's the table. And that transition is meaningless. You're not. It's supposed to be an energy neutral thing. The hoop comes down, hits that little ramp, or a little transition from the ramp to the horizontal, and that's not supposed to be an issue for us. And we're told that this height here is height capital H. And we're given some kind of structure. Okay. And the problem is to see what happens when this hoop leaves the table with a certain velocity. It's the same velocity it ended the ramp, coming down the ramp. and then it goes out there, and then it does the usual gravity thing, and ends up right there on the ground. So this is a first unit kind of a problem. This is things flying through the air under it's a free falling object. Okay, horizontal distance. Well, let's sort it out the way we have done in the past. We'll talk about in y, and then we'll talk about what happens in the x direction. And what do we have? We have VF, VI, YF, YI, A, and T. T is what we need, because once we have the time that it will take to fall that distance h, that's also the time it would take to translate some distance that we're trying to find. Okay, so VF, this is in the y direction now. So the V final we don't know, the V initial is 0. The y final is 0, the y initial is h. Acceleration is gravity. So the sign of that may come into question, I don't know. And the time is most interesting to us, I think, of all those things. Okay, now in x, let's talk about VF and VI. These two things in the x direction are going to be identical, and that's the velocity that we got coming off the ramp, which was, let's see, the square root of GL sine theta. And in x, it will continue to be GL sine theta because there is no acceleration in the left-right direction. Okay, so the XF now, not the YF, but we don't know that. That's our target in the problem. The initial height is, or the initial position is 0. Okay, so we're going to consider that location there to be 0, and we're going to see how far it is to, where the ball comes to rest, or the hoop comes to rest. Okay, acceleration is 0, and then the time, whatever we found over here, is going to be the time that we find right in there. All right. Well, let's do a kinematic to figure out the time it would take to fall. I think I can work up in this region right in here. Oh, what do you want to use? How about y final equals y initial plus VIY time plus 1/2 GT squared. I think that would do it for us. There's other possibilities, but this should work. Okay, the y final is 0. Y initial was h. VIY was 0. And then plus 1/2 GT squared. Here comes a chance to make a little mistake. Let's put negative h over this side, multiply it by 2, that's because this is divided by 2, then divide by g, and that arguably carries a negative to save our heads from exploding from trying to have a negative under a square root. And this would be time, and then I would have a big square root over that. Just catch up in scoring guidelines here. So that gets us time is equal to the square root of 2h over g. All right, and you've done that a million times. But I did see more than one student mistakenly, I think, had the g in the numerator on that. It's okay. Okay, there's our time. Now let's talk about in the x direction. So in x, how about x final equals x initial plus velocity in the x direction times time, plus 1/2 at squared. We know there is no acceleration in the x, and it begins at 0. So that just comes down to x final equals velocity in the x direction times time. Here comes substitutions. X final equals, where was our velocity? Square root of GL sine theta, and we're multiplying that by the square root of 2h over g. And when you do that, multiplying radicals, we can consider them all to be under a single radical. So that goes away, and I have 2h squared. No, that's an L, excuse me. That's an L right there, not an H. That's 2L. So my answer becomes square root 2LH sine theta. 2LH sine theta. And that's our answer for part C. Okay. Now comes the think piece. And the think piece means you have to, ponder what's going on, theory. You can't always do math when you have one of these problems. Sometimes you can justify your answer with math. Sometimes you can't. What are we told here? We're told suppose the hoop is now replaced by a disk having the same mass and radius r. How will the distance from the edge of the table to where the disk lands on the floor compare with the distance determined in part C for the hoop? Less than, greater than, same as. The answer is greater than, and let's think our way through that. So this is part D, and the answer is greater than, so it's going to go farther. And why is that? Well, we know that as the average distance of mass from the center of rotation goes down, the I goes down. So I can say that I of the disk has got to be less than I of the hoop. And maybe you remembered I for a disk. Was it 1/2? I can't remember. 1/2 mr squared? I think so. But we know that. We know that's a relationship right there. And if you go back to, I guess we're still playing bells today, even though there's nobody in the building. Well, that's not true. There's actually a lot of people in the building. I think there's going to be some basketball. There's going to be some cleaners out there. I'm trying to find the kind of the best place in our previous work to trot out I. Well, here's a place we can make some sense of it. You see right in here where we had, this is back on this approach where I did torque is force times moment arm. We had this expression right here. We said that force times radius is equal to I times alpha. Well, the torque doesn't involve I, does it? The torque was just a question of the friction times the radius. Okay? So in this problem, friction times radius. And in our second approach, let's see if I can spot a good place to capture it there. Well, we had a similar idea. We had torque, a different expression for torque, force times moment arm, and that's weight times moment arm. So the weight times the moment arm equals I alpha. So if you look right in here, this component never changes. That's not under question. What we're saying, though, is if I goes down, and that remains constant, that necessarily means that alpha goes up. So to preserve that torque, and mathematically, if that goes down, which it does for a disk rather than a hoop, then that must go up. So the answers given in the scoring guidelines are something like a disk will have a smaller rotational inertia and will therefore have a greater rotational velocity. This will lead to a greater translational velocity, greater distance x. I consider that argument a little bit distant, but doable. Here's another one. The rotational inertia is less than the hoop, causing greater acceleration. That's one we just said. And more final speed at the end of the table. Okay? If it's accelerating greater, then it's going to be faster when it gets to the end of the table. Therefore, it would be going farther once it leaves the table. Oh, look, here's mr squared. When I is mr squared over 2, there goes 2/3 g sine theta. So you could do it if you remember the expression for I for a disk, mr squared over 2. So the disk will be moving faster. There's an example where you could use math, and if you used a correct expression for that, that would be a suitable argument. Now, there were some one-point answers. This is a 2-point response right here. You have 1 point for checking greater than, 2 points for a healthy argument. They did have some examples of 1-point arguments that weren't quite up to snuff. A disk has greater rotational inertia, so it will have greater kinetic energy and will therefore land farther from the ramp. That's an unproven stretch. That's a little bit much. Okay, I'm not even sure this is true. A disk has larger rotational inertia. No, it has smaller rotational inertia. The moment of inertia for the disk is smaller, therefore its rotational velocity is bigger, causing it to go farther. The problem with that one is this is rotational velocity, but it doesn't connect directly to, or at least as it's written here, it doesn't connect directly to translational velocity. You have to extend that argument a little bit. Less energy used to spin the disk than the hoop, so in the eye of the disk is less than the eye of the hoop. Therefore, you have more energy, to make this into a 2-point. Therefore, more of the total potential energy would convert to kinetic energy. You'd have to make that argument. Okay, and I'm going to give you a problem at the end of this that will ask you to travel the same thinking where it asks these questions a little bit more directly. Another problem, I think it's from 1986, I'll leave you with. Okay, so that was the first free response question. I hope my video is recording. Second free response question was, let's see, which one was it? It was, this guy, kind of the sort of the centrifuge idea. You're dropping a mass, causing this thing to spin around, and the setup is a light string is attached, that is attached to a large block of mass 4m, passes over a pulley with negligible rotational inertia, another name for I, and is wrapped around a vertical pole of radius r. Okay, so that pole has its own radius, lowercase r, if anyone's asking. The system is released from rest, and as the block descends, the string unwinds and the vertical pole with its attached apparatus rotates. The apparatus consists of a horizontal rod of length 2L with a small block of mass m attached at each end. Rotational inertia of the pole and the rod, that's the pole, that's the rod, are negligible. So those things are, they apparently have no mass. Okay, determine the rotational inertia of the rod and block apparatus attached to the top of the pole. B, determine the downward acceleration of the large block. And C, when the large block has descended a distance d, how does the instantaneous total kinetic energy of the 3 blocks, these are spinning, this one's falling, compare with the value 4mgd? Check the appropriate space below, justify your answer. And then there's a part D to this. On the second page, the system is now reset, and you have the same situation, except that these masses are now suspended by strings, I guess. And as this thing begins to fall, this thing begins to spin, and those masses go outward, and they also go upward. So that's going to be the key to figuring that part out. Okay, so back to the first part. I think I can. Well, let me start with a clean sheet so that we're not entangled with the end of that previous problem. Give me a second here, staple that. Okay, this is problem 2, called Mech 3. I forget what year that was from, but you can tell me somewhere. Give me just a minute. I need to find my other scoring guidelines here. Whoop. Okay. All right. Let me get my pen go. Oh, I left my pen over there. Okay, second problem, quick sketch here, so I can refer to it on the page. Here's I guess we're calling that the rod. I'll give it a little thickness because it has a radius. It doesn't have any mass, but it does have a radius. I love these magical things that we get to do. Okay, so that's the so-called rod, and we have these little masses down here, M and M. There's a string wrapped around there, and it goes to a pulley. Pulley has a mass of 4m. And that, by the way, resulted in a lot of mistakes in grading or in student work. And this whole thing is on some kind of a table. So that's on the strut, maybe. Okay. Let's see, what else do we know? I don't think it says so, but the pulley has no mass either. That pulley right there is intended to be massless. That didn't enter into the problem. Funny, I don't see that mentioned in the... Oh, yeah, it does say it, top line. Pulley with negligible rotational inertia. Okay, so first thing, determine the rotational inertia of the rod and block apparatus attached to the top of the pole. Okay, so what do we know? We know that I is equal to the sum of mr squared. Now, two things to point out. This is what we use when we have discrete masses. So this is for discrete masses, not for a continuously solid object. When it's a solid object, that's when we get out the integral version of this. We have to integrate mr squared, and you get that whole dm business going on, and it's much more difficult. But the other thing I want to point out is that sigma right there. It is the sum of terms. So you have to show that that's part of what's going on here. So maybe I can do it right over here. I have, and this was distance 2L, which was clever of them, right? That means that every one of these is just a single L, like that. So I guess thank you for not involving a fraction. Okay, so this is equal to ml squared plus another ml squared, and that equals 2ml squared. So that's I of this little arrangement at the top. And that was worth 3 points, believe it or not. One for the formula, and the other thing said for a sum containing a term of the form ml squared may include extra incorrect terms. This is funny, but the point was not awarded if the expression does not contain an ml squared term. So that was about just being dimensionally correct, making sure you have the right sorts of terms here. But we know that. That was a nice, fast way to pick up 3 points. That's part A. Part B, determine the downward acceleration of the block. Here's where we get into some trouble. This is where I would call this the hardest part of the problem. So let's do a free body diagram for the block. We have 4mg downward, and we have tension upward. Now, we also have happening right in here a torque that involves tension. I'm just going to write T right there, so we're also thinking about torque equaling I alpha. So let's first do a second law thing with the hanging mass. The sum of forces is equal to mass times acceleration. I'm putting that in quotes because I'm about to do some substitutions that matter. The sum of forces, let's describe downward as positive, because that's the direction of motion, but again, that's arbitrary. So 4mg minus tension, so tension is up, is equal to 4ma. That 4 was missing on a lot of student work on this test. So that's a little gotcha, and it led to, not too damaging a downgrade, but that was a thing. Now, I look at this and I see two unknowns. I don't know what the tension is. I don't know what the acceleration is. So that means that we can't use it. We can't use this as our final way to get an answer. We need another expression that involves tension, and the one that's going to come into play now is going to involve torque. So let's look at the sum of torques. That's a bad sigma. The sum of torques is equal to I alpha. And then while we're at it, because we're always concerned about leaving money on the table, why don't we also say that acceleration, linear acceleration, is equal to R alpha. Now, I use lowercase r. I think there's only a single r in this problem. It's a lowercase r, and it's up here. It's the r of the pole. Good so far? Okay, so let's talk about torque. Torque is tension times radius. So torque is tension times radius, and that equals the I that we got right up here, 2ml squared, 2ml squared times alpha. So alpha equals A over R. So A over R. Okay? Now, check this out. We have the very same two unknowns in this expression that we had in this expression, which means we're in business, right? Isn't that kind of the story of life? If we have two equations with two unknowns, we can happily make it work. I look at the clock here. I see we're up at 45 minutes. I'll finish this problem, then we'll take a little break, or I can ask you to stop the movie and take a little break, so we can not get too fatigued here. Okay, so I need to bring all these things together. What do you think? How about if I solve this one for t? I'm going to solve that one for t. So if I bring the t over to here and I subtract this over here, I end up with this expression. T is equal to 4mg minus 4ma. I know that's factorable and so forth, but let's leave it alone for a moment. But let's solve this one for g as well, or for t also, and then I can equate this expression with a t expression. So here's the torque expression solved for t. ml squared a over r squared. Off the screen. Okay, so I just solved this expression for t, and I solve this upper expression for t. And now we can equate these two things, and we will have just a single expression for a. And a is what we're after. We just want, some expression for a. Okay, let's see how we do. 4mg minus 4ma equals 2m. Those are all lowercase m's, by the way. In the original drawing, every time you see m, it's the same m. And there are four of them right there. So I don't need to worry about uppercase and lowercase. We're all speaking the same language here. L squared a over r squared. I don't think I can stand it anymore. I'm going to factor out the 4m. Actually, why don't we just divide both sides by m? No more m. 4. Oh, you know what? I'm dying to factor out the 4, but I know I have to untuck the a, so somehow I'm going to have to involve the a over here. So I don't want to do that yet. So 4g minus 4a equals 2l squared a over r squared. Okay, well, let me bring the a over to the right-hand side and then factor out bring these a's over to the right-hand side, factor out the a. Well, it's a little bit messy, but we're okay. So 4g is equal to 2l squared a over r squared plus 4 times a. What a mess, but I want to factor out a here. So this becomes a times 2l squared over r squared plus 4, and that is 4g. Oh, boy. Yeah, what a mess. So a is equal to 4g divided by 2l squared over r squared plus 4. Now, if you got to that point, that's sufficient. It can be cleaned up, not happily. In fact, it kind of violates a rule of simplification. But I'll show you what they did. They multiply everything by r squared over r squared. Top and bottom by r squared, r squared, r squared. And when you do that, you end up with, oh, this is awful. Sorry, no. Let's not do that, but let's, yes, do this. So now we have a common denominator down here, and you get A is equal to 4G over 2L squared plus 4R squared over R squared. This is kind of ridiculous at this point. Okay. So A is equal to 4GR squared over 2L squared plus 4R squared. Now, if you divide everything by 2, you get one last simplification, which is 2GR squared over L squared plus 2R squared. So there's A. Now, here's what bugs me about this. I don't know, math teacher thing. I hate when you claim to have simplified something and you end up with the same variable appearing two different places. That kind of bugs me, but I don't see another way to improve on that. But like I say, if you got to this point right here, anything in here, forget my red right in there, but anything in there would be a sufficiently good answer. Okay? All right, now, that was the hard component of the problem, I think. So that, just to review what we did, we set up a free body diagram for the hanging mass. We recognized, Newton's second law in translation, and then we used Newton's second law in rotation. Same law, two different settings. And then we did this is really our rolling, that's a rolling motion idea. We hadn't called it that yet. And then we kind of cobbled those two equations together, finally teasing out A all by itself. So that was kind of a mountain to climb, so you understand. And it's talking about, now we have the energy problem. And what does it say? It says, when the large block has descended a distance d, how does the instantaneous total kinetic energy of 3 blocks compare with the value 4 mgd? Check the appropriate space below. Okay, the answer is equal to in this case. So let's talk about why that is. This is part C. And we have our stick, the masses, the rope, the pulley, the mass, the hanging mass, which is 4m. So if we drop this a distance d, maybe we should put the label up there, isn't that representative of a potential energy loss? Okay. So let's look at an energy equation. We would say, before the problem begins, U plus K rotation plus K translation is equal to, this is before, is equal to U afterwards, plus K rotation plus K translation. Okay? Well, beforehand, it's up here. So imagine that this is our zero-base plane for potential energy. So it begins with potential energy mgh. Well, m is 4m, g is certainly there, and h is the distance d. So that's 4mgd. That's where, so that comes from in the problem they're talking about. There is no rotation, there is no translation to begin with. There is no gravitational potential to end with. So this is all the initial setting, and this is the final setting over here. So if this drops down to zero potential, this term goes to zero, and I'm left with this statement that the potential energy at the start is the same as the sum of the two kinetic energies at the end. So it's the same as. So that's this question right here. How does the instantaneous total kinetic energy, those are those terms, how does it compare with this term? It's exactly the same. Okay. Now, the problem changes a little bit. We've been going at it a long time, so let me get off the podium here quickly, and then you guys can take a break, come back, and we'll finish going through this. Okay, now here's the only difference. In this problem here, these things began right there, and they ended, I wish I showed that a little bit better, they ended swinging upwards. So this represents a change in the potential energy of the system, gravitational potential energy of the system. So let's go back to this statement like we had up here. U plus K equals U plus K plus K. This is rotation, this is translation. This is rotation, this is translation. Okay, we began with 4mgd for potential. Nothing going on there at the start. But when we ended up here, this potential energy increased because, where am I? These little dudes rose a little bit. So they gained gravitational potential energy. It was not a zero once this thing had descended d. It was, it was 4mgd plus something else. So this is a positive quantity. I'll just write positive quantity. That U term is not zero. It increased. So if this is a constant and this goes up, these must come down. Okay? Those two things, something about them, must have gone down. The total kinetic energy is now less than it otherwise would be. And let me just make sure I haven't spoken with forked tongue. I think I'm okay on that. The answer is less than, and correct justifications such as the small blocks rise and gain potential energy. The total energy is still 4mg, therefore the kinetic energy must be less than in part C. Okay? All right, take a break, maybe a 2-3 minute break. Come on back in your chair, pause. Substitute, I apologize, I don't know your name. If you could pause the video right now and then start it up in a moment after everyone gets back in the room, and we'll go through that third problem. Okay. Pause for the cause. Okay. All right, next, let's do the third problem. Let me see here. We'll do this one. Just number my sheets, save them. Okay, the third question was this one here. It was the one where you have the beam or a long uniform rod of mass m, length L, supported by it's uniform, nothing funny going on there, supported at the left end by horizontal axis into the page. So that's a rod or pin going right into the page, and then by the thin vertical thread, so the rod is horizontal. Moment of inertia of the rod about the axis at the end, so it's about here, is ml squared over 3. I think we proved that once upon a time. And then express the answers to all parts of this question in terms of m, l, and g. There's another invitation to keep g as g. Don't go making that into a number if you don't have to. Determine the magnitude and direction of force exerted on the rod by the axis. I'm trying to find that force right there. Now I want to show you, I accepted anything, this part A was 4 points as I recall, 4 points, yeah. And I accepted any answer that said that half of the weight is supported by the pin or by the axis and half of the weight is supported by the thread. The weight is mass times gravity. So if you had mg over 2, I didn't dwell too much on how you got that mg over 2. I just said there's 4 points. But let me show you how to prove that, because the mere intuition is not really good enough. This is our third question. We have the rod. I've got to do my drawing. We have the rod we have the string, and we have the pin. Okay. Now this thing has M, and we're told it's uniform. Now uniform, that means that we could set up a free body diagram, and if I had a free body diagram of this thing, I would say, you know, it's still showing forces where they're applied. This is mg, this is, I don't know, tension of the string, and this is the force of the pin, or force of the axis. What do they call it? The axis. The tripartite axis, the axis of evil, all the famous axes in the world. Okay, so if you look at that, it seems kind of self-evident. Each one's holding up half. But the better way to do it is what I showed you the other day when we did a little moment about the sum of torques equaling 0 as being an equilibrium condition. So if we say the sum of torques is equal to 0, we have to choose a pivot point. So I'm going to choose this as the temporary center of rotation. Okay, so for the purpose of summing torques, I'm going to do it about there. Okay, so think positives and negatives. I know we have that. So that looks like a positive torque because it would cause it to rotate counterclockwise. That would be a negative torque. So positive minus negative. It looks like we have mg. There's the force, but what's the moment arm? The moment arm would be L over 2 because it's halfway along there. So mg L over 2 minus force of the pin, and its moment arm is L. So L, and that equals 0. Okay, there's a positive torque, there's a negative torque. And what do we do? Let's factor out, I guess we can factor out the L, huh? What are we solving for? Force on the pin? Couldn't we divide both sides by L? 0 divided by L is still 0. So I can make the L go away. You know, divide by L, it's still a 0. And I have mg over 2 is equal to, oh, this is immediately solved, Fp. And there's our answer, Fp equals mg over 2. So this is a nice thing using the sum of torques, and that's an equilibrium condition. So we also know the sum of forces is 0, and that would have been how you would solve it if you did it this way. Okay. I think that would do. You know, the problem if you do it with sum of forces, you have Fp plus T equals mg, but nobody actually says that that doesn't really prove that Fp and T are the same thing, or there's no proof of that. So I think sum of torques is the better approach on that. Okay, part B, we want to, it says the thread is burned by a match. I love that. That's, you know, let's tell a story. It wasn't cut by a scissors, it was burned by a match. For some reason that's important. For the time immediately after the thread breaks, determine each of the following: the angular acceleration of the rod about the axis, so this thread goes away and things starts to fall; the translational acceleration of the center of mass of the rod; the force exerted on the end of the rod by the axis. Okay? All right. Second here. Okay, let's start with, that was part A. Let's start with part B, with looking at torque equals I alpha, because we're looking for angular acceleration. Yeah, and we have, so that means we're looking at torque about the axis, huh? So this is I about the axis times alpha. And remember, alpha is common throughout the part. Everything, just like omega, is common throughout this horizontal rod here. Doesn't matter where you're standing, the angular acceleration is the same, as would be the angular velocity, you know, in terms of radians per second or radians per second squared. Okay. So what is the torque that we have here? This went away. Now we have mg L over 2. So mg L over 2. Yeah, mg L over 2. Well, sorry, I want to set this up left side, right side. So mg times L over 2 is equal to, and what was that, ml squared over 3, ml squared over 3 times alpha. And in this case, we need alpha. We don't need to go to A just yet, but we're about to in the next part of the problem. What can we do here? We can cross out the, get that up on the screen, make it bigger. We can cross out the m's. Anything else? We can cross out 1L. What do I have left here? I have alpha, solving for alpha. So alpha multiplied both sides by 3. I still have a g. On the bottom, I have a 2, and then I would divide by that 1L. And there is your answer, 3g over 2L. That's the answer to part B. Okay. Does it make sense dimensionally? You know. Well, it's tough to sort it out because it looks on the face of it like it doesn't make sense dimensionally, but it's okay. That would give us, because that's gravity is meters per second squared. That would be meters squared per second squared. But anyway, don't worry about it. Okay, part C. Now we need, part C is pretty straightforward. We're looking for the linear acceleration of this point here. Remember, this point is now falling. So the linear acceleration, A equals R alpha, which equals is L times alpha down here, which is 3g over 2L. There goes the L. Now it really does have units, recognizable units of acceleration. That's 3/2 of gravity. And this is kind of like, oh, sorry, let me make sure I have the right part of the problem here for a second. Sorry, hold on. No, that's right. 3/2 of g. We did this. This is the same problem as when we sort of imagined taking a meter stick. I think I put a cap on the end of it, and I let it fall from one end, and we saw that the tip is accelerating faster than gravity. So 3/2 gravity. Clean that up a little bit. 3g over 2. We're not surprised to see that as faster than gravity can do its thing. Okay, part D. The force exerted on the end of the rod by the axis. Okay, so here's the rod, and we're asking, once this thing releases, how much force is upwards by the rod? So I think that's a bit of a puzzler. Would it go up? Would it go down? Let's talk about Newton's second law. Let's do part D right here. So the sum of forces is equal to mass times acceleration. We're going right back to Newton's second law. What are the forces up and what are the forces down? Well, should we pick downward as positive here? I think we've sort of gone that way before. So we have mg, and this is in the y direction, by the way. So force in the y direction. We have mg down minus force of the axis up, and that equals mass times acceleration. But that's acceleration of the center of mass. I just want to make sure they made that point. Give me just a minute. I want to correct something that I did incorrectly. In part C, it's asking for the acceleration of the center of mass. Center of mass. I mistook that just now, and I took it for the acceleration of the tip out here. So let's go back and change the radius from L to L over 2. Okay, so I'm going to go to here, and this is a true statement. R is no longer L, it's L over 2. So that introduces another 2 right there for a better final answer of 3g over 4. So this is A of the center of mass. And I made a mistake when I explained that a second ago. A of the center of mass. Okay. All right. Now I feel better. Okay. So here I can put 3/4 g right into there. I have mass. What do we need to do? I guess a little algebra here. Solving for FA. FA is, if that were over there, this would become mg minus MA center of mass, and I'm actually back into full capitals now, capital letter G, capital letter M, excuse me, equals mass times, let's see, G minus 3/4 G equal, let's see, that's 4/4 minus 3/4, that's mass times gravity over 4. And that's our answer. For force for the axis upwards is 1/4 of the weight. 1/4, sorry, I'm off the screen. 1/4 of mass times gravity, right there. Seems funny. I struggled with that answer. I said, ooh, could it really drop that much? And I said, well, maybe I have a sign mistake in here, but if you reverse that sign, it becomes way more than weight, and I couldn't justify that. That seemed like a lot of a drop right there, but that's the right answer. Okay, now the next question is determine the angular velocity of the rod as a function of theta, the arbitrary angle through which the rod has swung. We get extra points for grammar. That was a well-written sentence. Okay, I think the best way to do this would be to look at the energy. Let's look at it from an energy standpoint. If we can go from energy to let's go from energy to rotational kinetic energy, and that will let us go to angular velocity. Okay, so here's part E, echo. U plus K equals U plus K plus K. And there's our, I think I've been putting rotation first, translation, rotation, translation. That's arbitrary. You can reverse those orders any way you want. So let's look at what would happen if I pick some arbitrary angle theta. What do you get? Here's angle theta. This thing is pivoting around there. This is length L. And what happens to let's call that L over 2, because this is the center of mass, and we're talking about the center. I know this carries on down there. There's more stuff down there, but here's the center of mass, which I care about. So that makes this distance here, the change in height, let's see, this is that over that would be the sine of that. So my H, for the purpose of potential energy, is equal to L over 2 times the sine of the angle. H equals L over 2. Or maybe you want to call that delta Y, something like that. Okay. So this left term, this is the initial stuff, this is the final stuff. This would be mg L over 2 sine theta plus 0 is equal to 0, because this is where we're temporarily anyway defining our zero potential location, plus 1/2 mv squared, 1/2 I omega squared plus 1/2 mv squared. Okay, so it does have two kinds of energy going on. But wait a minute. Let me explain something. In the long run, we're going to make a decision that this thing is only rotating. It is not translating. So in the instant, I agree this thing is pivoting, but the center of mass is regarded as not moving anywhere. If I just built this object in a lab, it would sit there and it would oscillate, but we don't regard the center of mass as going anywhere. So that's the way they approached it. They said that term is not usable in this setting. And they just set this equal to that, so that the motion in question here is only rotation. Unlike with rolling motion down a ramp, where there actually is a distance traveled. Okay, so that's a little bit of a thing to, when I first saw that, I said, is that true? I said, yeah, that is true. Okay, so let's equate some stuff. We do have a value for I. So mgl over 2 sine theta is equal to 1/2 times, what was it? 1/3 ml squared times omega squared. And we're only looking for angular velocity. So all we need to do is clean this up and then solve for omega. A little algebra stuff. Okay, the m can go away, the m can go away, NL can go away, NL can go away. I don't think we can do too much more than that. A little quick cleanup step here. I have g sine theta over 2 is equal to L omega squared over 6 . Okay, so I'm solving for omega. Omega is going to equal the big square root. 6 times, multiply both sides by 6, that gives me 6 over 2, which is a 3. G sine theta over L. 3G sine theta over L. That's the answer right there. Okay, if you want to, if you have anything you want me to show you on the scoring, I'm happy to do that, but let's do that either the next time we meet or when we're, you can see me outside of class if you want me to explain the little 1 point, things that you see on your test. As always, check my math, make sure I haven't shortchanged you when I'm counting up all my little 1s and 2s and 3s and 4s. Okay. All right, I'm going to stop this video and then I want to show you another couple of things. No, I tell you what, I'm just going to roll right in on this. This is, I know I'm already up to 1 hour and 17 minutes on this one video, which is some kind of record. The one thing I want to show you, you know what, I'm going to hit pause while I get out some stuff here. Okay, I think we're back, if I understand the camera controls okay. Okay, I wanted to look at question 18, which is one of your assigned problems, and I apologize. I should have covered this idea the other day. It didn't pop into my head. It goes like this. This problem says we're heading, it involves us. It says we're heading straight toward the summit of Pikes Peak. An airplane of mass 12,000 kilograms flies over the plains of Kansas at a nearly constant altitude of 4,300 meters, 4.3 kilometers, with a constant velocity of 175 meters to the west. Okay? What is the airplane's vector angular momentum relative to a wheat farmer on the ground directly below the airplane? And then part B, does this value change as the airplane continues its motion along a straight line? So they're telling you ignore the fact that the Earth is curved, or is a sphere, pretend it's a flat Earth. What is its angular momentum relative to the summit of Pikes Peak? Well, we got to figure out what that is in meters, I guess, huh? So let's look at look at how that goes. So it's going to the west. So here's the airplane, and it's traveling. Let's see, 175 meters per second, and it's traveling to the west. So I'm showing it going to the left, and down below here is the farmer. He's a stick figure, so maybe he farms sticks. As my wife, I get to clean the kitchen after we do dinner, and sometimes I have to use steel wool. And my wife is a knitter. I always wonder, if I have all the steel wool, could she knit me a steel sweater? I think that would be a good idea. Okay, what is the airplane's vector angular momentum relative to the wheat farmer on the ground? So this is part of a longer path. And it turns out that we have the mv vector, you know, and that exists. It's the same vector. It doesn't. It's like any vector. You can sort of just move it around as needed. It's still the same vector because it has direction and magnitude, but its precise location sometimes is not important. But then the radius is no different from the altitude. Okay, so that makes sense. If I take mv times that radius, so L equals mvr. That equals mass of this thing, which was 12,000 kilograms, 12,000 times the velocity, which was 175, and times the radius, which was 4,300. We have to keep SI units, so that's meters, and you end up with whatever your answer is. I don't have that answer right in front of me. I won't take the time to go through it. But what would happen if you tried to calculate it as if the plane was over here? And that looks like a radius, but this is kind of like when we talk about moment arm. Didn't we say when we do a cross product, it's the magnitude of the first times the magnitude of the second times the sine of the angle in between them? This over that is a sine of that angle. So you get the very same total answer. Sorry, I can't stand it. Well, I won't take the time. But you get the very same total answer. You'd just be using a different value for r, and you'd be using a different. You have to involve the sine or whatever angle that is. But that's right there is the same distance. So just as with moment arm, it's really the perpendicular to the vector involved that matters. If we just figure out what mv is and figure out that perpendicular distance, sometimes it's easy to just give it to you. Other times you may have to do, hack your way to it geometrically, but that remains the same thing. Now, I'm going to go out on a limb here and say that is it possible that 4,300 kilometers is the height of Pikes Peak in meters? I'm going to ask Siri. Hey, Siri. Hey Siri, what is the height of Pikes Peak in meters?
Pikes Peak is 14,108 feet above sea level.
Could you please convert that to meters?
Okay, I found this on the web. Could
really?
you please convert Pikes Peak to meters? Check it out.
Yeah, okay. Anyway, what I suspect they're asking about is part C, somewhere over here to the west, here comes the airplane. I think it's going to pass through the peak of Pikes Peak, redundant, and I think you're supposed to recognize that there is no moment arm, and so that would turn out to have zero angular momentum relative to the summit. That's a guess. That's plausible, though. I think that's what they're trying to get you to recognize, that there is no moment arm, or radius, really, radius of rotation. Therefore, there is no angular momentum. Okay, I'm going to stop right there. That was long. Thanks for being patient as we went through that. I know we didn't advance the ball very far today by getting into section 3, which is angular momentum of rotating rigid object, and then the big change there is L equals I omega instead of L equals mvr, but it's the same concept really. And then we didn't get into conservation of angular momentum, which is section 4. So we're going to have to save that for our next visit. Once you enjoy the weekend. No, I guess it's Monday for you. So I'll see you on Wednesday, and we'll call that good for now. Thank you.